Welcome to the starting line. In our last module, we performed chemical surgery on our molecules. We gave them wings through derivatization. We made them fly. But let's be honest, a bird in a storm is just a lost bird. To turn that flight into data, you need a controlled environment. You need a stage where every gust of wind and every degree of heat is calculated to the millisecond. Welcome to the world of gas chromatography. Welcome to the molecular racetrack. Think of your GC instrument not as a box of wires, but as a precision racetrack. Your molecules are the racers, and today, you are the race director. We aren't just here to hit the start button like a common operator. We are here to master the architecture of the race. We're going to navigate the engine, the gate, and the thermal stage to ensure every molecule reaches the finish line, the detector, exactly when it's supposed to. The roadmap of mastery. Our mission today is divided into 4 strategic sectors. Sector A, the carrier gas, the invisible engine that drives the flow. Sector B, the injector, the flashpoint, where liquids turn into ghosts. Sector C, the oven, the master of time, that controls the speed of the race. And finally, Sector D, the liner, the forgotten stage where purity is either preserved or destroyed. Let's look at our engine first. Chapter A, the lungs of the system. In GC, the carrier gas is your mobile phase. It's the wind at the back of your molecules. But not all wind is created equal. The carrier gas must be chemically inert and highly pure. Most labs use helium. It's the reliable sedan. It's safe, it's inert, and it's predictable. But actually, here's a specialist's secret. If you want to win the race faster without losing resolution, you look at hydrogen H2. Look at this Van Deemter curve. Nitrogen is too slow for modern needs. Hydrogen allows for much higher flow rates while keeping the height equivalent to a theoretical plate low. It's like upgrading your system to a turbocharged engine, but it comes with a risk. It's flammable. A button pusher is afraid of hydrogen. An oven master understands how to use hydrogen generators to cut their runtimes in half. Respect the lungs or the system will choke. Chapter B, the flashpoint. Your sample arrives as a liquid, but it needs to enter the race as a gas. This happens in the injector. It's heated to 250 degrees or more. In an instant, flash. Your 1 microliter of liquid expands 1,000 times in volume. This is the most violent moment in the life of a molecule. As a race director, you have to decide on crowd control. This brings us to the split versus splitless decision. Split injection is for the VIP's high concentration samples. We vent 99% of the sample out of the split vent and only let 1% enter the column. Why? Because the column is tiny. If you send the whole crowd in at once, they'll trample each other, causing column overload. Your peaks will look like rolling hills instead of sharp mountains. Splitless, on the other hand, is for the trace detectives. We close the vent for about 60 seconds, forcing every single molecule into the race. Mastering this switch is how you balance sensitivity with precision. Chapter C, the master of time. Now we reach the heart of the machine, the oven. Most people think the oven is just a heater. Wrong. The oven is a time machine. In GC, the concentration in the gas phase is a function of its vapor pressure. The temperature doesn't just heat the sample. It determines the partition coefficient. It decides how much time the molecule spends resting on the stationary phase versus running in the carrier gas. Have you ever seen early peaks that are sharp but late peaks are broad, flat blobs? That's an isothermal error. You kept the temperature the same, so heavy molecules got lazy. A specialist uses temperature programming. We start cool to sharpen light molecules, then ramp the heat, sometimes 20 degrees a minute, to kick the heavy molecules toward the finish line. 90% of your chromatographic resolution is won or lost in how you architect this thermal ramp. Chapter D, the forgotten stage. Before we conclude, we must talk about the liner. It's a simple glass tube inside the injector. It costs $5. But a dirty liner is the #1 project killer. It's where active sites live, microscopic craters that trap your molecules. If your peak looks like a shark fin with a massive tail, check your liner. Ipro replaces it before every major batch. You wouldn't run a Formula 1 race on a track covered in glass shards, would you? Summary. The race is managed. Today we've mastered the invisible engine, carrier gas, the crowded gate, injector, and the time machine, oven. We've moved from being operators who just watch the screen to architects who control the gas phase. Remember this mantra. Precision isn't about the machine, it's about your mastery over the variables. You are no longer just injecting a sample, you are directing a molecular symphony. You've built the racetrack and managed the wind. But what about the track surface itself? The race is won or lost, based on how the molecules grip the column walls. Join me in our next unit, Module 4-2, the chemical coding, where we learn how to match GC columns to molecular polarity to achieve peak perfection. I'll see you at the finish line. Any questions on the engine, gate, or stage?